So in this problem, we have an infinite wire. So I'm doing review question number 5 for exam review 3. So question number 5 says you have an infinite wire placed along the x-axis with a uniform charge per unit length of lambda equals 5.2 coulombs per meter. Find the electric field at a distance of 3.4 meters from the axis. So what we're told, right, is that we have an infinite wire, and we're told that this wire has a charge on it, uniform charge, and we're told that lambda is given by 5.2 coulombs per meter, positive, so coulombs per meter, and find the distance. So we're at a distance of, so we're told that distance, let's call it r. R is given by, find the electric field at a distance of 3.4 meters. Sorry, my eyesight's not that great. So here's our wire. So find the electric field at a distance of 3.4 meters. And so the idea behind it, right, is that we're calculating the electric flux. So we create a Gaussian surface. Okay, so the Gaussian surface is going to be a Gaussian cylinder. Remember, when I say a Gaussian surface, it just means it's a closed surface. So it's some kind of a closed volume of space. So here is our Gaussian surface. I'm using the dots to represent something behind the board. Okay, actually I should have done the board so the dots show here too. But anyway, and we're going to be at a distance of r. So when charge is located, notice positive means there's positive charges along this wire. So here's our wire. Now the electric flux is going to be radially symmetric along that line. And so we expect that the flux, the electric flux, remember how we thought of the electric flux. So mathematically we can define electric flux in terms of E dot A, some uniform electric field and some vector area as the flux. But this is a mathematical definition. So the correct way of thinking as a physicist, right, is it represents the number of field lines that penetrates that surface. So think of the number of field lines that penetrate the surface as the flux. So the total flux, right, if you remember, is the number of field lines penetrating the surface. And remember, the field lines are uniformly distributed in the cylinder, so all the field lines are spread out. So it'd be equal to the radius r, and we'll assume that this Gaussian cylinder has a length L. We just made those up. So the electric flux, right, would be, by mathematical definition, would be equal to the electric field E times A, but the electric field and the area, right, of every element in that surface, right, is the same direction. So the dot product, which is the magnitude of E times the magnitude of A times cosine of theta, but theta, the angle between them, right, is actually 90 degrees. I'm sorry. Theta is 0 degrees, and so cosine of 0 is equal to 1. So this is really E times area for every little patch element of area element. So that means that the electric field times area across this, factor out the electric field, and we get the total area of that circular portion of the cylinder, the circular skirt of that cylinder. And so this would be equal to 2 pi r, the perimeter of that cylinder, times the length L times E. That's the electric flux. But Gauss's law basically says that the electric flux is also equal to, proportional to the charge within that cylinder. And the cylinder length, right, happens to be lambda. So this is, the cylinder length is L, and lambda is 5.2 coulombs per meter. So we're talking about the amount of charge that's inside is lambda times L. And this is proportional, and remember, most textbooks use divided by EO, but remember, I would like you to remember it's 4 pi k times lambda L. So I'm going to equate both these equations together. So electric field is equal to I'm sorry, electric flux is equal to, that's theta, phi. Phi is equal to, let me get another marker, I'm going to throw this marker away. Is 2 pi r L, which is also equal to 4 pi k times lambda L. So remember, k is our Coulombic constant. And so we can cross out the pi's, we can cross out the L, and we can divide by 2 on one side, and we get that the electric field, E, is given by, so the electric field is given by 2k lambda over r. That's the electric field. So remember, I don't expect you to memorize equations. I expect you to construct these problems always from start by using Gauss's law. So this is an example of cylindrical symmetry. So there's also planar symmetry and there is spherical symmetry. So they all have similar problems. So if you had to do this in terms of calculus, this is quite complicated and we'd have to spend a little bit of extra work trying to do an integration. But it's not a complicated integration, but still it's much more complicated than using Gauss's law. So the electric field is given by, is it on the board? Yeah, it's still on the board, good. 2 times k times lambda over r. So 2 k, Coulombic constant, is roughly 9.0 times 10 to the 9. We're using standard units so we don't waste time like putting the actual units in. That's for earlier classes. Lambda is given by in coulombs per meter, so it's standard units, 5.2 divisible by a distance, a radius of 3.4 meters, again standard units. So whatever this is, the answer happens to be in newtons per coulomb, standard units. Okay, so this is question number 5.